Chapter 4.1, we're going to be going over exponential functions and starting with laws of exponents. So for this section, the b, if we see a b, that's going to denote a positive number, and x is obviously going to be a variable. So if we have the function f of x equals b to the x, that is an exponential function because the variable x is in the exponent, and the b we call the base of the exponential function. And this is technically some review here for the laws of exponents. We have several different laws. The first one's called the product rule, and that says if you multiply common bases, you combine them into one base by adding the exponents. And the next one is if you have a negative exponent, you make it positive by putting it in the denominator. Next one's the quotient rule. If you're dividing common bases, combine them into one by subtracting the exponents. Next one, power to a power, or power of a power. If you have a power to a power, combine them by multiplying. And if you have two factors, both to the same exact exponent, you can multiply them together and then raise them to the exponent. And last one, if you are dividing two different bases raised to the same exponent, you can combine them and raise that quotient to that exponent. So let's go over some examples of this. Let's use properties of exponents to write the following expressions in the form 2 to the kx for some constant k. So we need to rewrite these with base 2, and then the x is in the exponent, and k is just going to be some number. For the first one, we have 4 raised up to the 5x over 2. So for this one, in order to write this as a base 2, we have to rewrite 4 as a base 2. We know that 4 equals 2 squared, which is base 2. And then using the rule where it's a power to a power, you have to multiply these two exponents. So that's going to be 2 raised up to the 2 times 5x over 2. The 2's cancel, and we end up getting 2 raised up to the 5x. So that's in the form 2 to the kx. In this case, k is 5. Next one, we have 2 to the 4x times 2 to the negative x, all raised to the 1/2. So for this one, we are multiplying common bases. So to combine those, we have to add these exponents together. 4x plus negative 1x is 3x, raised up to the 1/2. And now this is a power to a power, so we multiply. 3x times 1/2 is just 3x over 2. So in this case, our k value would be 3 over 2. Next one, 8 to the x over 3 plus 16 to the 3x over 4. This one's a little more complicated. We can rewrite both of these factors so they have base 2. 8 can be rewritten as 2 cubed. And 16 can be rewritten as 2 to the 4th. And now these are both powers to powers, so we multiply. 3 times x over 3, the 3's cancel and we're left with 2 to the x. For the second one, the 4's cancel, 4 times 3x over 4, and we're left with 2 to the 3x. And now we have common bases being multiplied. Add the exponents. X plus 3x is 4x. And last one, we have 10 to the x over 5 to the x. We are dividing, and there are different bases. But what we can do, since they're raised to the same exponent, we can rewrite them like this. 10 over 5, all raised to the x. And now we can simplify. 10 over 5 is 2. So that's just 2 to the x. Okay, so these are just exponent rules, technically something we have done before. So that brings us to exponential functions. And there's going to be two main types of exponential functions. These are going to be in the form y equals b to the x. There's going to be two main types that we're going to look at. The first one is when the base is greater than 1, and then we'll see what the second one is in a second. So in this case, we have f of x equals 2 to the x. The base is 2, which is greater than 1. So let's plug in some x values and see what happens here. Let's plug in an x value of -2, -1, 0, 1, and 2. And since I have room, let's just plug in a 3 also. So if we plug in a -2, that's 2 to the -2. And 2 to the -2, move this over, 2 to the -2 is 1 over 2 to the +2, which is 1/4. That gives us the xy coordinate 2, 1/4, positive 1/4. If we plug in a -1, 2 to the -1 is 1/2. That gives us this xy coordinate. If we plug in a 0, anything to the 0 is 1. So 0, 1. We plug in a 1, we get 2. We plug in a 2, we get 4. And we plug in a 3, we get 8. Okay, so now let's plot these xy ordered pairs here and see what this looks like. So -2 1/4 is going to be something like this. -1 1/2, 0 1, 1 2, 2 4, and 3 8. And if we connect them, it will look like this right here. So this is an exponentially increasing function. And we'll see on the next page there's actually a horizontal asymptote at y equals 0, but we'll see that on the next page. So this is what happens when the base is greater than 1. It's exponentially increasing. Now let's see what happens when, in this case, the base is between 0 and 1. So the base cannot be negative. It will not be an exponential function. In order for it to be an exponential function, the base has to be either between 0 and 1, or it has to be greater than 1. So it can only be positive numbers other than 1. If it was equal to 1, if we had something like y equals 1 to the x, that will always equal 1, which is not an exponential function. That's why 1 is not included. Okay, let's do the same thing now. Let's plug in a couple numbers. Let's do negative. I'm going to do -3, -2, -1, 0, 1, and 2. And I'm doing that just because I know what's going to happen when we plug it in. And let's plug in -3. 1/2 to the -3 is 2 to the +3. And that's going to be 8. So that's -3, 8. Plug in a -2. That's going to give us 4. Plug in a -1. That gives us 2. Plug in a 0. Anything to the 0 power equals 1. And we plug in a 1 and get 1/2. And plug in a 2. We get 1/4. And now let's go ahead and plot these xy ordered pairs here. And that's going to be -3, 8, -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4. And connect them with a smooth curve. It's going to look something like this. And this is our function g of x equals 1/2 to the x. So since the base is between 0 and 1, the base is 1/2 here. This is an exponentially decreasing function. And hopefully you can tell it looks like a mirror image over the y-axis compared to the one that we just did. That's because it is. We could rewrite 1/2 to the x as 2 to the -1 to the x, because 2 to the -1 is the same thing as 1/2. multiply those exponents, that's 2 to the negative x. This negative means reflect, negative on the x means reflect over the y-axis, which is exactly what we did up here, from up compared to the one up here. This function up here, f of x, was 2 to the x. If we negate the x, we reflect it over the y-axis, and it ends up looking like this one right here. Okay, and then for this last thing, we have some properties of exponential functions. As long as they're in the form f of x equals b to the x, so nothing else going on, no adding, subtracting, multiplying, dividing, anything, just b to the x, we have these certain properties. There's the domain is going to be negative infinity to infinity, all real numbers, and the range is 0 to infinity. The y-intercept is going to be at 1. It's going to be 0, 1. And then 3 and 4, we get these two separate cases. If b is greater than 1, so if b is greater than 1, it's going to be exponentially increasing. And if b is between 0 and 1, it is exponentially decreasing. So you can see that they're both crossing, supposed to be crossing, right here at the y coordinate of 1. And the last couple things here, there's a horizontal asymptote at y equals 0. So like I mentioned, there's technically a horizontal asymptote for these right here on the x-axis at y equals 0. So HA horizontal asymptote. That's because it'll never equal 0, and it's never going to end up dropping down into the negatives. And then for this one right here, 1-to-1 function and has an inverse. 1-to-1 means we can draw a horizontal line anywhere, and it's only going to intersect the graph once. So it passes the horizontal line test, and that means it has an inverse function, which we're going to see our logarithmic functions in the next section. Okay, so that's kind of just a review for exponential functions, chapter 4.1.